Good afternoon. Am I audible?
Yes, sir.
Okay, so let us get started. Uh, so I hope the presentation is visible. Right?
Yes, sir.
So we have been discussing about templates, which are very important extension in C++, which allow us to write some generic code where one or more type variables may be used, so that algorithms that can generically apply to multiple types can be coded just once in terms of a generic code using one or more type variables, and then used, instantiated based on a specific type at the call site, either explicitly or implicitly. We have seen different situations for that, so that we get the actual code for every case generated as a overloaded function by the compiler. And then though they are called based on the parameter types or the actual explicit instantiation of types and so on. We have also seen that we can have some uh, partial or complete specialization of templates in case we need a different algorithm for a specific type, right? We saw that in terms of doing the max function. We could write a generic max for int, double, char kind of types, whereas we specialize to write a different algorithm for the char star C style string type. We did a separate one for the complex type and so on. Right? So that was the basic idea of the template, which we saw in terms of the functions. What we'll discuss today is use of these templates in terms of classes. Classes can also be templatized. They can be defined in terms of type variables. So a much bigger paradigm can be covered. So this is what we saw, just recapitulating that functions like search, minimum, maximum, swap can be templatized. Now we'll see that the classes like list, queue, etc. can also be templatized with the same intention. The intention remains to be code reuse, not having to write very similar code for different types, but rather writing them in terms of type variables and getting the actual code generated. This is what we saw in as in slide 5. Now, class template has a primary role in terms of code reuse in data structures. Function templates primarily allow you code reuse in terms of the algorithms. But if you have an entire data structure, which could be one of the very common standard data structure, or it could be a data structure that you have created for your specific application, but can be used with multiple types, we will engage the class template mechanism. So for example, let's take a look at solution of several problems need stack. We know last in first out, like reversing of string, converting infix expression to postfix expression, evaluation of postfix expression, depth first traversal of trees, and so on. And in every case, we can see that we need variety of different types to be used. Right? But we will need a stack. Conceptually, we will need a last in first out data structure for each one of these cases. Similarly, there are several problems that require queue or first in first out, like task scheduling, process scheduling. Again, we need queue, but we have different element types to be used for managing these queues. So solution of several problems also need list or ordered lists, like implementation of stack queue, implementing object collections in different ways, and so on. So the examples could be plenty. These are the very common generic problem situation examples. Your specific case will have examples of your kind. So the issues in data structure is data structures are generic. They have the same interface, they have the same algorithm. But when it comes to implementation, they become different because you have different element types. Right? So that is the basic problem we are trying to address. So here is just for further elucidation, there is a comparison of stack of characters on left and stack of integer on right. If you compare this code, you see they are exactly the same, except at these 3 points where I have written like char. You have to write the array container for the stack here being used. You have to write that the array is of character type elements. On the other hand, on right, this array of integer type elements. Similarly, when you push, you are here pushing a character, here you are pushing an integer. When you top, you get a character out, here you get an integer out. Except for that, these types being different for the elements, everything else, the concept, the interface, the algorithm, everything is same. So the question is, can we combine these stacks by using a common type variable t? So that is what we will do in terms of the class template, which will be parameterized with type. Parameter that could be parameterized member functions also. Instead of going through the abstract description, let me just take an example. So again, the class, the stack class, you write it in exactly the same way as you did before, except wherever there was a reference to the element type, whether char or int, you replace that with the type variable t. So you write it. This is an array of 100 elements of type t. You push an element item of type t. You get from the top an element of type t. And that's the only thing. And on top, like you did in case of the function template, we write the same thing. We write template class t. We could write template type name t also, which tells the compiler that t is a type variable, right? So that whenever we need a particular element type for a stack, we could instantiate t and get the actual stack generated. Right? Now, obviously, t is any type variable. It could be a built-in type. It could be a user-defined type. But there is some trait that we need for this element t. Certainly, we will need constructor, destructor. And we need copy assignment operator, because without copy assignment operator, as you can see here, when you are pushing, we are copying this element to the array location. So this copy will not be possible unless we do have a copy assignment operator in the type t that we are passing as a variable, right? And again, we are using uppercase S to name our stack because there is a standard library component called stack, which is written with the all small case letters. Now with this stack defined in the header, stack.h, now we are writing a reverse string example. This code is very well known to you, that you keep on pushing elements into the stack, then you keep on popping them naturally till the stack gets empty. Naturally, you will get the string reversed. Now, to use the templatized stack, you make an instantiation of the type variable t exactly in the same way you had been instantiating functions. So you write the class name, and then within corner brackets, you write the type name. So this will tell the compiler that it will use the template of stack in stack.h and generate a complete code of stack class which has element type as char. Right? You do not have to write that. The compiler will generate that and use the functions of push, empty, top, pop from that generated code. So you have a huge reuse here. Similarly, going to slide 11, there is another that we are trying to do for postfix expression evaluation. So there's a postfix expression given 1, 2, 3 star plus 9 minus. So what you keep on doing is you keep on pushing these elements in the stack till you come to an operator. Once you come to an operator, you take the topmost two elements and operate them and push back the result. So if you try to evaluate this, 1 will go in the stack, 2 will go in the stack, 3 will go in the stack till you get star. And then you evaluate the top 2, that is 2 and 3 you take out, and you multiply, you get 6, that goes into the stack. You get plus, so you have 1 and 6 below that, so you take out, you add them, you get 7, which goes in. So you have 7, then you push in 9 and you get minus. So you take out the top 2 elements, 2, 7 and 9, and do the operation. So naturally, this is how your code will look like. That if it is a digit, then you just push it, find out what is the digit and push that. If it is not, then you take out the topmost 2 topmost elements, remove them and get them as 2 operands. And then depending on the particular character that you have got, the operator symbol, you compute the result and push it back. So this is the algorithm to evaluate postfix expression, and that uses a stack of int. And you did not have to write that, because using the same template from stack.h, the compiler will create a stack of type int code and use the methods from that code in this particular main function. Right? So that is the basic purpose of the stack, basic purpose of the class template. Now, naturally, as I said, that the template parameter must have some traits that they have to follow. Otherwise, you cannot instantiate with that type. For example, they may be of user-defined type. They may be themselves be parameterized types. They may themselves be having further template parameters. But it must support methods used by the template function. So you have to look at what are the required constructors, those must be there. What are the required operator functions, those must be there. What are the necessary type needs to support. So your type variable has to be a type, has to be instantiated with a type which is supporting these traits. That is the important part. Right? So we saw that in case of function templates also. You saw that in the last module. Similarly, for class template, we will need these kind of traits. Now, a class template can be done with a forward declaration. And with a forward declaration, that is, you can just say that this is like you can do a forward declaration for a class. You can do a forward declaration for a templatized class as well. As you do the forward declaration, the compiler knows that the class exists, but compiler does not know the definition of the class. So with a forward declaration, you will not be able to instantiate an object that needs a complete definition of the class, but you will be able to use a pointer to that class or a reference to that class, because they do not need to know the details inside the class, right? But class template will have to be instantiated before any object of that instantiated class can be used. Right? So continuing on the example on slide 15. So I'm just writing it in a different way without the .h file where everything was given at the beginning. I'm making a forward declaration here for the class stack, saying that it has a parameter, type parameter t. And then I'm defining a reverse string function, which takes a reference to a stack of character type. So it takes that reference, and it is perfectly valid to do that, even though I have not defined the stack, because I am not creating an instance. And then actually I write the stack definition, templatized stack definition here. And then only I'll be able to write the main, which instantiate a stack of char as S. So this needs the definition to be there. Otherwise, I could define the reverse string without actually defining the stack. And then finally, I use the reverse string call to the reverse string. The reverse string function itself has been forward declared. So later on, I go and define the reverse string function. Right. So this is how you can manipulate on the class stack definition. Naturally, like the function, the class templates can also be partially instantiated. For example, let us suppose that you have a student class which has a roll number and a name, two things. And you are planning to use two types, T1 and T2 for them. So let's say, just for the sake of it, that roll number, say, can be integer, but the name can be either a string type in C++ or just a char star of C style string. In any of that is possible. So you write the first template definition of the student class, saying class T1, class T2. And like you do in function parameters, you are also doing default template parameter. That is, if nothing is specified for T1 and T2, then it will be taken as int and string. Okay? So this is one definition for the student. Now I partially, I do a partial instantiation. So what I do is I instantiate the type T2 here. So I say student class now is T1 and char star, not T1 and T2. That was here. So T2 I have instantiated as char star, and T still remains to be a template parameter, a type parameter. So here, out of the two parameters, one I have instantiated. So this is what is known as partial template specialization. So if I want to use char star as my name term, and you can see that naturally the constructor will change for that. When I'm using string, I can just do a copy because string has a copy constructor. Char star does not have a copy constructor for C string. So I have to do that whole lot of code to allocate space and then, make the actual copy and put that pointer to name and so on. So it differs in terms of the implementation. So I have different algorithms for the constructor based on the general template or the specialized, partially specialized template. Then if I use it as int string, then this is int string. I'm explicitly saying that if I'm using it as int, then it is int string again, because T2 is default of string. If I do not specify anything, then it is again int and string, because both have been defaulted. If I just say string, then it is string, because T1 becomes string and T2 is defaulted as string. But if I say int char star, then it does not match the general template, because I have specialized it. The T2 has been specialized for char star, partially specialized. So it will match the part of T2 here, and then T1 will be int, and it will use the second version of the template. So in this way, you can give different flavors. So one is you are making your class generic by using template parameters, and at the same time, you could partially specialize or fully specialize the template type variables to provide different algorithms for the member functions of your class. Right? So this is the beauty of the template. So this is another example of a list, which is a template class of list, which can put an element to the list. It can find the length. It can find, that is search, if an element exists and tell you whether it exists or not. Internally, it uses a vector container to keep the elements. So you can build a list of any type with these interface of find, length, and put, and use it as a list element. So suppose you are now trying to define a new data structure set. Right? So you have templatized, you want to do a set of any type. So you have templatized it with type parameter t. Right? So you have a length, you have find. Now you have a define the add function as a virtual function. That is, you are defining a polymorphic base class. And internally, you keep the items as a list. In the set, add function of the set, which you define here, you do a find, and then you, because in set, you cannot add an element more than once. So what you do a find with the value that you have to add. If it is already there, you do nothing. If it is not there, then you will put that value and in that list. So items dot put, items is of type list t, so it will use the interface of the list and put that item in the list. And you say that well, for length, I do not define it. Again, the function, I'll return the length of the list class, items.length. Similarly, for find, I'll use the find of the list class, and that is how these two will get implemented. Keep in mind that when you are here inside the class definition, you are just calling it set. But outside of the class definition, it has to have the full name. The full name of the class is the class with the type that the template has. So when you want to talk about add outside, you do not say that set : add. You say set corner bracket t, because set corner bracket t is now the name of the class. Set corner bracket t : add. Right? So that is what you are doing in every case. And you write template t to tell the compiler that this is a templatized, this is a method implementation of the templatized class set. Now, as set has been done as a polymorphic base class, I can do a specialization on the set. I will say that set will have a bound, right? A minimum maximum bound. So here I'm mixing inheritance with templates, right? So I'm making a polymorphic definition, a template definition for bound set with type parameter t, and that is derived from the parameterized definition of the base class set. So it will inherit all the public and protected members of set t. And when you instantiate t for a bound set with certain type, the base class set will also get instantiated with the same type. So it is saying it is a bound set is a public function which can set the bounds here, because the construction by default of inheritance will happen through the constructor of set, and then you are separately trying to set the minimum and min and max values through the bound set constructor, which will in turn call the constructor of the set. So I have this is how you will set in the constructor. And for add, you have a different logic now. So add of set was just to find and add it to the list if it is not there. Now we will check if it is within the bound and then add it to the set, which is a parent class. So in this way, you can actually have a hierarchy of classes which are templatized, so that their element types or certain parts of the class can be defined in terms of type variables. And when you instantiate Then based on those types at the instantiation, the actual classes, the codes for the actual classes will be generated by the compiler. And accordingly, when I'm going to slide 20, I have instantiated with bound set int, which will also instantiate a base class of set int inside. And then I have instantiated another set int instantiation of the set class, a pointer to that, basically. Not instantiated, rather I have created a pointer to that because I want to use the virtual function functionality, and using that I can now make use of the add function to add, and it will, given that it is currently pointing to a bound set instance, it will invoke the add of the bound set function, right? So this is the kind of things you can do using the template, and this is heavily used in the standard library components. And we will see in assignment 4, we will ask you to write code based on this concept of templates as well, and use them along with the inheritance, right? So we have talked about templates in C++ in terms of functions as well as in terms of the classes. So this will give you a different kind of polymorphism. One kind of polymorphism which we have seen is the polymorphism in terms of overloading and overriding, and finally getting into the runtime polymorphism of virtual functions and dynamic cast and so on. And this is another kind of polymorphism, which is called the parametric polymorphism, because you are again writing one definition of a function or one definition of a class, and actually having multiple different type-based use for the same, right? So that's the template mechanism. Let me go back and ask if you have questions. Any questions, friends? No questions? Everything is clear? Okay, then let me go back and now we are getting very close to the end of discussions on the C++ language and variety of program development and implementation mechanism, which help you do very good quality of object-based object-oriented programming based on an object-oriented design. So before I close, I would intend to talk about two other things. One is what is known as a functor. This presentation has not been shared with you. I will share this. So let me just introduce you what is the concept. Functor, as the name suggests, sounds like a function, right? So what is a function? In general, we say something that can be called in C or C++ is a function. Right. Now, how do I recognize it in a code? When do I say that I have a function call? When I see an occurrence of a pair of parentheses following a name and possibly having 0, 1 or 2 comma separated parameters. So we have been accustomed psychologically to identify this as a kind of call to something else, which has to take the parameters and do some computation. But we never thought about this as an operator itself. Like multiplication takes 2 parameters, multiplies and gives you the result. Addition takes 2 parameters, adds them, gives you the result. Output streaming takes a stream and your element, streams it to the element and gives you back the stream, right? So these are all operators we have seen. Similarly, this is called the function operator, which takes the parameters and the function and applies the function on the parameters and gives you back the result. So applying the function itself is an operation. We have never looked at it that way. We said that every operation is a function, but the fact that you are calling a function is you are doing an operation, right? So that is this operator. So any callable entity is something which has a function call syntax. That is, it has this operator parenthesis support. And such objects are often called function objects or functors. So there are several callable entities in C++. You have function like macros, right? We have function macros naturally, unless you know it is a macro, they look just like functions if you look at the call site. So you have function like macros, you have C functions which are in global namespace, or they could be in specific namespaces in C++. You have member functions of classes, which could be static or non-static. You have pointers to functions, that is pointers to C functions. You have pointers to member functions, static as well as non-static. You can have reference to function. I mean, they act pretty much like the constant pointer to function. And you have function objects or functors, right? So let's see what. So much of this you know. I will quickly just recap and take you to the most interesting thing, which is a functor. So what you have in general, you have every function is also a pointer. What does that pointer mean? That pointer means the address where the first executable statement of the function occurs, right? So we say that a function pointer is a variable which has the address where the function begins. So if you call that particular address, then the function starts executing. So it points to an address of a function, an ordinary C function, a static C++ member function, or non-static C++ member function, and points to a function with a specific signature. I mean, all function pointers are not same. They differ in terms of the signature. That is the list of calling parameter types. They need to know the return type and what is the convention of the call. Which is it a C call or it is a C++ call, and so on. So you have these function pointers which you have seen as a part of your PDS. So I can define a function pointer, ptr to function. To say that it is not a function but a function pointer, I put a star. So if I say pt to function, then I have a function pointer. If I do star, I have the actual function which takes one integer and 2 characters. That's a signature, returns a character, whatever that function is. And then I have some function, say do it, which is taking an int char and does some operations. Operations are not important here. So I can assign this, the function that I have, I can take the address of it and assign it to the function pointer. Actually, a special syntax is, since a function is synonymous with its address, I can do the assignment without the ampersand operator also, because a function actually means that address. So I can also do this assignment. After I have done this assignment, this function, come to the last line on slide 7, I can derefer that function pointer and get the function, which is star pt2 function, and call it with the parameters. Right? I can compare function pointers also. Right? So this is typically what you have seen in terms of the function pointers in C. We have used that in terms of doing certain calculator application, doing that your staff salary application, and so on. So you could use function pointers directly, or you can give the function pointer a type alias, do a type def, and accordingly you could just use a function to assign to a function pointer, or you could use the function pointer type to define a function pointer variable and assign the function there. And if you do directly use the function pointer, you have to dereferences. If you use the type, then you can just use the function name and call the function. Right? So that's the function pointer. Now, you can have function pointers references in C++ also. You can define a function pointer of a member function. All that you need to do is to qualify that this function pointer is for the member function in class A, and then take the function fully qualified function name and assign to the function pointer, and then subsequently you can use it based on the typical call syntax that take the object dot the function name will invoke the member function. So these kind of function pointers are possible. So the question is, what can you do with the function pointer? You can assign an address to a function pointer, assignment or initialization. You can compare two function pointers, see whether they're same or different. You can call a function using a function pointer. You can pass a function pointer as an argument to another function. You can return a function pointer. You can make an array of function pointers. Right? These are the kind of things that you can, these are the operations that you can do with function pointer as a type. Right? So function pointers replace switch and if statement, and it can help realize user-defined lead binding like virtual functions and so on, to implement callbacks and stuff like that. I will not go, I mean, I will share you the slides. I'll not go through these examples in depth, like using switch, using function pointers to implement a switch. We have already seen this example. Or dynamic library, I'll just leave for now. Let us talk about quick sort, so which we also have talked about, that if C has provided a quick sort, then how do I write that code? Because quick sort did not know the element type in general. So you could take the element array as a void star and specialize it, actually cast the type when you call the quick sort. You could set the number of items, you could set the size of every element, but how do you define the comparison? So you pass a function pointer. So these kind of function pointers are called callback pointers, because when you this function pointer in qsort is not known. So you have to define a function and provide it in the place of the function pointer. So quick sort, you are calling quick sort, that is a forward call, and quick sort will call back the CMP func that you have defined. So this is a callback use of the function pointers. And obviously you have seen the cases of virtual function, where function pointers are heavily used to get the dynamic polymorphism. Right? Now function pointers are good, but they do not have a value semantics. I mean, they cannot be taken as a complete object. Their type checking is weak. For example, if I want to have two different types of function pointers which have identical signature, say mult and multiplication type of function pointer and addition type of function pointers, both take int and return you int. Both take a pair of int and return you int. So their function pointer signatures will be identical, but they are indistinguishable in C. Right? So you cannot have this kind of stuff done in function pointer. Also, it does not encapsulate the parameters. What it means is, when you have a function call, you need all the parameter values computed at that point of time, and immediately the call is made. Right? You cannot say that I will compute first parameter at some point of time, second parameter at some point of time, and then actually call the function at a later point of time. Right? That kind of. So that is where you introduce the concept of smart functions or function objects or functors. These are functions with a state. Functions are just execution, right? You call, the stack frame is created, parameters are copied or passed by reference, control is transferred to the function executes, makes the return value, copies it back or gives it by reference, unwinds the stack, and control comes back to the caller, right? So they do not have a state. Next time you call, it's a different call, right? But function pointers but the functors are functions with a state. They can encapsulate C, C++ function pointers within them. They can use templates. They can engage in polymorphism, everything. And every function pointer has a type of its own. Right? So what is a function pointer? A function pointer is what is a functor? A functor is a class with 0 or more private members which can store the state, and it overloads the operator function. That operator function executes the function. So let us see what it would mean. So how do you overload the function call operator? So you overload in this way. So you say operator. Now, you have not seen the syntax, do not get confused. This is not a typo. What is being said, this is like if you are talking of operator plus, you'd write it as operator plus symbol, then within bracket you would write int comma int. Similarly, here the name of the operator or the symbol of the operator is a pair of parentheses. So this is your function call operator, and this next pair of parentheses is for the parameters that this function will take. When the operator calls the function, what parameters will be taken? So the second line on slide 25 is a function call operator with two parameters, int and int. Good. A concrete code. Look at this code. The first part is simple. I have an adder function. Takes two integers, adds them, returns. Done. Second part is a class adder functor, where I do not have any other member. I have only a public overloaded operator function. So operator function takes two parameters, int a and int b, adds them and returns. Now the main use. X is initialized with 5, y is initialized with z, and then you call adder function with xy. This function is called, x and y are added, 12 as a result, initializes z. Now adder functor is a class. So now I instantiate adder functor AF. Now look at this syntax, which will kind of amaze you, because you have never used an object and in the context of a function call notation. So you say AF as if AF is a function. What is actually happening? What is actually happening? We know what happens in overloaded case. It is the corresponding operator function that actually gets invoked. So AFXY is actually AF dot operator function XY. So it calls this function. This call actually is a call to this function. So it computes A and B, add of A and B, and gives you the result. Right. So it is encapsulated as a part of the object. So it is a behavior of the object. The behavior of the object, when you use the function call notation on it, is to invoke that function call operator and execute that function. Right? So, okay, before I get into more examples, you can now see that since I have an object, it is possible that when I'm constructing adder functor, I can construct it with these parameters. The constructor could take the parameters and set them in private members. And my operator function could just take no parameter and still execute. So I could make my parameters, one or more of the parameters, as private data members in the functor class. So they will decide, I mean, once I set the parameter, they decide the state of the functor. And then whenever I invoke the function call operator, the actual function execution happens based on that state. Right? So just to show you some examples from STL, like I want to fill a vector with random numbers. So what I have done is I have defined a vector of type int. You can now understand this notation very well, that vector is a templatized class in STL, component vector. So where every element type I'm now saying should be int. I'm calling it v, and I've passed a default size of 100. There's a vector of 100 integers. Then I'm using a template algorithm which iterates from v.begin, which is the beginning of the vector iteration, that is iteration on v, that it starts at the 0th element and goes up to the end, that is goes up to element 99. And for each one, it generates a value by calling this functor. Rand is a functor, it's a function object. So generate takes the third parameter, which is a function object, and as it iterates on the vector from beginning to end, every time it calls that functor and fills in the value. One possible use of functor. Classical sorting example. We saw how quick sort had to be written. It's very, very difficult. Now I want to write a sort, and I have a sort template, function template given. So based on that, it takes two iterators, the beginning of the vector until the point it has to go. I've said the vector is of type double. So the whole of that issue of Q sort, having to know the element type, the size of every element, number of elements, all these are relieved. All that you are doing, that you have a container and you are taking iterators on the container. But still you need the third, last component, that how do I compare two numbers of this type? So I will pass a functor here. So how do I get that functor? There is a functor template defined, which is binary function. It has three template parameters. First two, it is saying binary function. So this is a template for a binary function, where the first two parameters tell us the two parameter of that function. And the third template parameter tells me the type of the return value. So when I write instantiate binary function template by double bool, it says that I'm going to create a functor which takes two double values and will return a bool. So now my function operator takes two double values, double x, double y, and will return a bool type. And within this, I have defined the comparison algorithm, where I have, though it is double, I've said, no, I'm just not comparing just the number. I want to sort them based on their absolute value. So I've done fabs x and fabs y. So this whole thing is now a class. So then what I do, I define a class less mag. I'm calling it a struct, which means it's a class having everything as public, as a specialization of this functor. So less mag is a functor which inherits this function call operator. So what I have done here is I have instantiated that function less mag within, because it does not have any other parameter. So I just instantiate it, this functor object. So what will happen? Sort, when it iterates from begin to end, every time it calls this functor, which means actually this function gets called. And the comparison happen according to my algorithm. So this is another example of how functors are used heavily in STL. This is one where the earlier two examples did not have a state. But this is one where I'm defining a function with a state. I'm saying that I want to define a functor adder which will add elements and retain the sum. So it has a member variable called sum. And what is the function operation of this functor? Is it takes an element and adds to the sum. So the function operator takes an element double of type double and adds it to the sum. Right. So this takes one parameter double and returns a value void. So this is a unary functor. So I use the template of the unary function double, which is a parameter type, void, which is the return type. I derive my adder object, adder class from this, and I construct the adder object by initializing sum to 0. Because now it has a state, I have to define the state. Earlier, I did not have to do this. So then I have a vector of double, and I use the template algorithm for each, iterating from the beginning of the vector to the end of the vector, and it calls the adder. So what it does, that it for each element of the vector as it iterates from begin to end, it takes the element and calls its functor. So takes that element, calls the functor, means this function operation is called. So that element is passed as the double x here, and the sum is added to this. Please mute. Some of you have got unmuted. Please mute yourself. And then finally, I print the result. So you can see there are multiple cases of functors that can be used for your purpose. And the reason I wanted to talk about functors at least briefly is the fact that when you use STL, which you should be doing very heavily, the functors like this will be required almost at every stage. You will often see that the STL components and STL algorithms need a whole lot of use of functors, where the user has to take the generic functor like binary function or unary function, instantiate it with specialization or specialize it from the class instantiated, and creates her own functor class, and that use that functor object in the context of the application. Right. So I showed examples of simple functor like rand, which is just equivalent to a function call actually, because rand actually is a function pointer, or a two variable function without state, or here a functor with a state that can use. So I will close here. Let me see if there are questions.
Sir, can you explain how did the for each function which you had used pass the value to result?
Let me go back
I
to the
didn't
slide.
understand the syntax.
Sure. Please. Can you see the slide? Slide 28. Right?
Yes, sir.
Okay. So what for each does, these are actually STL has a component called algorithm. Right. So like you have vector is a container, stack is a container of stack type, vector is a container of practically unbounded array type, or you have queue as a container. Similarly, you have a component called algorithm, which has some generic algorithms. So what does for each do? For each takes two iterators, iteration begin, iteration end, which is clear. Then it takes a functor object, and what it does internally, it goes iterating from the beginning till the end, and as it picks up every element from iteration, it applies the functor on that element, which does the sum operation. And after it has reached the end, it returns that iterator, right? So this iterator, I'm sorry, I'm very sorry, it returns that functor. So here, if I compare with the previous one, say sort, let's say sort, if I compare with sort here, the functor does not have a state, so nothing changes. The functor state does not change. Functor here is more an algorithm, which is flexible, which is templatized. So every time sort needs to work compared to elements, this functor will be called on those two elements. But here in for each, you are doing something and accumulating that result in the functor. So the functor here is not only the algorithm of addition, but it also keeps your result. So what for each does, whatever functor, every time for each is actually using the functor, the state of the functor is changing because the value of sum is changing. So what for each will do, when the iteration comes to an end at v dot end, it returns you that functor. So what you get back is the functor object that was instantiated here. So you will get an adder object. And with that, you have initialized the result functor of adder type, right? So result is an instance of this struct adder class. So it is double is a data member of that, and everything is in public, so you can print double dot sum. The crux of the idea is for each does return the functor that you pass it, because it is it is written in a way that you do something for each element on the iteration and you collect that result in the functor. So it has to return you that functor, right? Does it make it clear now?
Yes, sir, it's clear now.
Okay, good.
Sir?
Yes?
Sir, is there any similarity with copy constructor? Functors are quite similar to copy constructors.
No. They are not doing any copy or anything. Nothing is happening on the object. They're just like we are saying that like any overloaded operator is an operator function call. This is also an operator function call. The only difference is the operation here is to call. That is a conceptual barrier. The operation here is to call that function operator on the parameters that are given.
Okay, besides the initialization,
Everything else is same.
instantiation.
Everything else is same. Everything else is same. I mean, any class or any class can be a functor or will be called a functor if it has overloaded this function call operator. Then it will be called a functor. But obviously, you create functors based on a certain use of it, certain type of states that you want to maintain. I mean, there are very detailed examples of functions with multiple states and different design patterns. Command pattern is completely based on this functor concept and so on. I'm not going to the details. I just want to convey because this is conceptually very different from a function call where we just say that it's a call, it's a jump. This is not that. This is something with a state where you are overloading the function call operator to get the syntax of the function call, but the semantics of a state-based function. That is the basic difference. Okay. Any other question? No. Okay, then. Thank you very much. See you again tomorrow morning, and we'll continue from this point.